question 3 gives us this setup, and in part A it asks us to confirm the refractive index of the glass from which the prism is made. So the key to that is to use this relationship, which is on your data sheet, that n1 sine theta 1 is equal to n2 sine theta 2, where these are the angles from the normal as shown. So we can put those numbers in. So if we call 1 the air side of things, we get that the refractive index of air, so if we make this air and this glass, the refractive index of air, remember, is 1, to a very good level of approximation, times sine of theta 1, which is 15 degrees, is equal to n2 times the sine of 10 degrees. And so we can trivially rearrange to get that sine 15 degrees divided by sine 10 degrees is equal to n2. And if we just find the numbers for those, that works out to be 1.49, which is what it said we had to show. Okay, in part B we're asked to then continue the path of the light as it passes through the prism. So it's coming in through here, so obviously it's going to continue along this line here until it hits that wall there. Now what happens there depends on the angle relative to this normal. Okay, so this is the normal relative to that boundary there, and so it's this angle which we need to know. So this is all just about using triangles to keep track of the angles and make sure you know what all of the relevant angles are. So it's told us that this angle is 45 degrees, and so if we think about this triangle here, in other words between here and here and here, this angle, if we just mark that on there, is 90 degrees to there plus 10 degrees, so that's 100 degrees. Okay, that angle there. And so we've got that plus that is 145 degrees, and therefore this is 35 degrees in order to bring the angles up to 180 in that triangle. And if that's 35 degrees, then of course this must be 55 degrees in order to that those two add up to your 90 degrees there. So that's what you need to do. You need to sort of figure out your angles like that. And the critical bit of information it gives us is that the critical angle from glass to air is less than 45 degrees. So here we're coming in at 55 degrees, so it's greater than the critical angle. That means we're going to get total internal reflection. So we're going to get this coming out like so. Oops, that's going to be coming out like so, where this angle, and this is the one you need to mark on again, is also 55 degrees. Okay, so those angles need to be marked clearly on there to show that you calculated it correctly and to show that you've got total internal reflection there. Now when we get up to this boundary, you can see fairly straightforwardly, I think, that you've got the same situation at this boundary as you did at that one, because if we think about the angles, this is going to be the one that we're interested in. So if this is the normal here to that boundary there, the question is, what's that angle? And we can work that out fairly easily, because we know that this must be 35 degrees, again to bring those up to 90, and we know that this is 45 degrees because it's that's the point about the symmetry of the prism, and therefore again this angle must in total be 100 degrees, and therefore that again is 10 degrees. Okay, so just to confirm what you probably realised anyway, just by sort of looking at it, that angle relative to the normal is 10 degrees, the same as it was there. And of course what that means is that when you get refraction out of the prism, that angle is going to be 15 degrees, the same as it was there, because here the light is coming in from air to glass, and here it's going out from glass to air, but the direction doesn't matter. This relationship still applies, and so you're going to get the same angle relationship, so 15 degrees on the light coming out. So in part C we have this situation with these two prisms of different refractive index pressed together like this. So we know what's going on in this half because that's the same as we already had, and when it moves into this prism it's moving into a region of lower refractive index, so we know that as the ray moves into here, this angle is going to be bigger than 55. It's going to move further away from the normal, so the light is going to be bent sort of that way. Very well. So it's going to be bent sort of that way a bit relative to continuing along here, and what we have to do is calculate the angle of refraction, and the angle of refraction means the angle between the refracted ray and its normal here. So this is theta. So let's call that theta 2, and then we can just apply the law of refraction again. So we know that n1 sine theta 1 is equal to n2 sine theta 2. That's the law of refraction which is on your data sheet, and on this side we've got 1.49 times the sine of 55 degrees, which is the angle from the normal on that side, is equal to 1.37, because that's the refractive index on this side, times the sine of theta 2. And as soon as you've written that down, then again you can see that it's easy to figure out what theta 2 is, because you just rearrange that to get 1.49 over 1.37 sine 55 degrees is equal to sine of theta 2. And if you punch that into your calculator, you get 0.891, which means that theta 2 is equal to 63 degrees is your answer. So that means that that angle is 63 degrees. C part 2 depends on this relationship, which again is on your data sheet. That's the definition of the refractive index, that it's the ratio of the speed of light in a vacuum divided by the speed of light in the medium that we're talking about. So of course we know what that is because the speed of light is what it is, and that's on your data sheet, and it tells us what that is, so it's trivial to solve for that. So we just rearrange that to get that CS is equal to C over N, which is 3.00 times 10 to the 8 meters per second, divided by 1.37, which comes out to be 2.19 times 10 to the 8 meters per second. And that's the answer. In part 3 it asks us to draw on then what might happen when you get to the boundary here and the light emerges again. It doesn't actually tell you that you have to calculate exactly what happens, and the fact that it uses that phrasing, a path that the ray could follow as it emerges into the air, is suggesting that they're not necessarily expecting you to do that. So we'll talk about how you would calculate it in a second, but actually to get the marks, I think all you have to do is to realise that here's your normal here, and the point is that as you move from this prism into the air, you're moving into a region with a smaller refractive index, because the refractive index of air is 1, and if you move into a region of smaller refractive index, the light will be bent further away from the normal. That's the thing you need to be clear about. So it's going to do something like that as it emerges, coming out there. And that's probably all you need, well, that is all you need to get the mark there. If they'd asked you to calculate it, then you could do that fairly easily in the same sort of way that we did here, because you know that that's 63 degrees because we calculated that, and therefore this angle is 90 minus 63, which is 27 degrees. We know that this is 45 degrees. And so this angle is 180 minus 45 degrees, which is 180 minus the sum of those two. So minus 45 plus 27 is 72. So 180 minus 72 is 108 degrees C. I keep saying degrees C. 108 degrees. And therefore, because that's a right angle here, we know that this is going to be 18 degrees. Okay, so that angle is 18 degrees. And that's the one that we need to know, because then we can apply the law of refraction. So if we want to know what this angle theta is as the light emerges into the air, we can just apply the law of refraction. So we've got that. So within the prism, we've got N1 is 1.37 times the sine of 18 degrees, we worked out was that angle there, is equal to N2, which is the refractive index in air, which is 1. So 1 times sine theta. And therefore we just get that sine theta is 1.37 sine 18 degrees, which, if you plug it into your calculator, gives you 0.4233, and you can therefore work out that theta is 25 degrees as it emerges into the air there. So you could calculate that and draw it accurately, but it didn't require you to do that there. The main thing was to make sure that you had it bending away from the normal, because it was moving into a region of lower refractive index. Okay, so question 4 asks us to describe the structure of a step index optical fibre, outlining the purpose of the core and the cladding. So you just need to, it's left a nice space for you there to draw a sort of simple picture, which is a best way to show the structure. So the idea is that you have something like that. And you just label that this is the cladding around the outside, and this is the core. Make sure you put the labels on the diagram, that's important. Step index just means that the material in the cladding has a uniform refractive index. You can get more complicated types of fibres where that's not true, but that's what a step index thing means. So then you've got to explain the functions of the core and the cladding. So the point is that the core transmits the light, and the way that you make sure that it travels through the core and doesn't escape into the outside is that you get total internal reflection. So that's the key phrase that needs to be in there. Total internal reflection occurs at the boundary with the cladding. And of course, in order to make that possible, the cladding must have a refractive index less than that of the core. Otherwise, obviously, you can't get total internal reflection. And those are really the key things then, to show the relationship in terms of how they're organised and just explain those basic things. It's also, though, worth saying that the cladding also protects the core from damage. Because that's obviously very important, because if you've got cracks and stuff in that material, that's obviously going to interfere with the transmission of the light, and prevent adjacent cores in a bundle, because fibre optics are usually used in bundles, so it prevents adjacent cores in a bundle from touching. Because if they did, then obviously light wouldn't be totally internal reflected, because the cores would be of the same material, so the light could just pass between one another. From one to another. So it prevents adjacent cores from in a bundle from touching, which would allow light to leak between them. Okay, so I think if you got all of that down, then you would definitely be covered. Part B is asking us about a pulse of light passing through an optical fibre. So what a pulse means is that if you imagine a sort of graph of the intensity of the light as a function of time, that basically the light's off, and then in an ideal pulse it would sort of instantly go on and then instantly go off again sometime later. So that's the principle of a pulse of light, in a sort of idealized way, and they're really important in the data transfer applications, because it's the transmission of pulses of light that all of that is based on. So their behavior within optical fibers is a big deal. Okay, so it's saying what happens as you pass light with a mixture of wavelengths through an optical fibre. And the key to understanding that is this definition of the refractive index, which is there on your data sheet. Because you can see from that because the speed of light in a vacuum is a constant, and therefore if the refractive index is different for different colours of light, which you can see it is from the table there, and it's worth knowing that the refractive index decreases as the wavelength increases. But you can see that from the table there. And so you can see just by trivially rearranging that CS is equal to C over N. And so the bigger the value of the refractive index, the smaller the speed will be through the medium. And because the speed of light is different, therefore, for red and for blue as it passes through the medium of the fibre, if they're travelling at different speeds, that's going to affect how long it takes for them to get from one end of the fibre to the other, and that's the problem here. Okay, so that is the key relationship, and what it tells you in a qualitative way is that because N is bigger for blue light, that means that blue light travels slower. Through the fibre. So what that's going to mean then is that if we draw a sort of simple picture of that, so here's your fibre, that as the light goes in, blue and red enter simultaneously, because the red light is travelling faster, the red emerges first, followed by blue, just because the blue's travelling more slowly. So if we think about the total light emerging at the end, it no longer emerges as a pulse with a very narrow time width, because now it's spread out by the fact that the different wavelengths are taking different lengths of time, so the pulse gets dispersed, gets spread out in time, and that's a bad thing. So it's something in general that you want to minimise. Now that's all it actually asks you to do in this question, is just to explain qualitatively what the effect of the different refractive indices for the different wavelengths is. But you could actually be asked to calculate that difference, so it's just worth looking at how you would do that. And you can see again the key is this relationship here, so we can get that the speed of light is in the medium is 3 times 10 to the 8 speed of light in the vacuum divided by the refractive index, and it gives you the refractive index in the question for the different colours. So we can say for blue light that C of S is equal to 3 times 10 to the 8 is the speed of light in a vacuum divided by the refractive index it gives us, which is 1.467, which comes out as 2.045 times 10 to the 8 meters per second. Okay, so that's how fast the light is travelling through the optical fibre if it's at the blue end of the wavelength range. If we do the same for red, we get 3 times 10 to the 8 divided by 1.459. Okay, so because we're dividing by a smaller number, we get a higher speed, which is 2.056 times 10 to the 8 meters per second. And because it told us the length of the fibre is 1200 meters, we can use those speeds to work out the time it takes for the light to get from one end to the other. So in the case of blue, it means that the time taken to go through the fibre is distance over speed, which is 1200 meters divided by 2.045 times 10 to the 8, which comes to 5.87 times 10 to the minus 6 seconds, or 5.87 microseconds. So that's how long it will take for blue light to pass from one end of the fibre to the other. If we do the same thing for red light, we get that the time is 1200 over 2.056 times 10 to the minus 8, sorry, times 10 to the 8 meters per second, which comes to 5.84 times 10 to the minus 6 seconds. So you could calculate, if you were asked to, the differences in the transmission time for the two wavelengths at the extreme ends of the spectrum. So then in part C, it asks for what you could do to reduce this problem of the pulse spreading out. So the first, most obvious thing you could do is to use monochromatic light. In other words, light where it all has the same wavelength, because obviously then this whole problem goes away. So that's the first thing to say. The second thing is to keep the cross-section of the fibre, the width of the fibre, down to a minimum. Because you can see that if you have quite a wide fibre like this, then the path of the light could actually be quite long, because the light may be sort of doing this, you know, with lots of total internal reflection. Whereas if you have a narrow fibre, it's going to be, you know, a shorter path length. because it's not sort of spending its whole time wandering across the fibre, because it's not got as far to go before it gets reflected again. And the narrower the fibre, the shorter the actual path length is going to be, and therefore that will reduce the time, the actual time to go through, and therefore will reduce the time difference, and therefore reduce the spreading out. That is very important technology. Very thin fibres called monomode fibres, and they are designed to with exactly that effect in mind. Okay, so that's the second thing you could do, is to use very thin fibres. The third thing you can do is, instead of just having a long continuous fibre, at various points you can stop and collect the pulse and basically push it back together again. In other words, you can detect the pulse and then retransmit it as a sort of something starting out as a perfect pulse again. So instead of having a long continuous fibre, you every so often have a sort of reading station which reformats the pulse correctly and sends it on its way.